Welcome to the AI Research Roundup. I am your host, Alex. Today we're looking at a paper from May 28th, 2025, titled VRAG-RL, which stands for Empowering Vision Perception-Based RAG for Visually Rich Information Understanding. So it tackles how AIs understand documents full of images and charts, a popular method called retrieval augmented generation, or RAG, which helps AIs find external information to craft better answers, really struggles with visuals. This paper uses reinforcement learning, a kind of trial and error training, to teach vision language models, which are AIs that understand both images and text, to better reason about visual data. And for those interested in the technical details, the authors have shared the code for this work. The repository has a full multimodal training framework, which just means it's built to handle both images and text. They've also included a demo you can run and instructions for building your own version of the agent. Alright, this first figure gives a great overview of the whole framework. The diagram shows the main learning loop, where the vision language model interacts with the search engine and a special visual perception function to answer a query. A key innovation here is the visual perception action space. This lets the model select a specific region of an image, like a chart on a document, and essentially zoom in for a closer look, moving from a coarse to a fine-grained view. The system learns using a sophisticated fine-grained reward function that scores the model on multiple things: how well it retrieves relevant images, whether its final answer is correct, and if it follows a consistent reasoning pattern. This detailed feedback is what helps the model learn to reason so effectively. And this next figure gives us a great side-by-side comparison. On the left, you have the traditional retrieval augmented generation method. It retrieves an image and just feeds the whole thing to the vision encoder, which is the part of the model that processes the visual data. This can be inefficient. But on the right, with VRAG-RL, the model can actively perceive the image. It can decide to select a specific region, crop it out, and then re-input just that detailed section for a closer look. This coarse-to-fine process is what makes the information gathering so much more precise and effective. So building on that idea of effective information gathering, this next plot explores a really interesting trade-off. It shows how the model's accuracy changes depending on how many reference images it's given to work with at once. We can see that performance improves as we go from 1 to 3 images, peaking at an accuracy of 56.4%. But after that sweet spot, giving the model more images actually starts to hurt its performance, likely because of the added noise from less relevant visuals. This result highlights that simply adding more information isn't always better. Okay, and this table of main results really drives home how effective this selective approach is. It compares versus VRAG-RL against other methods on several benchmarks like slide VQA and long bench, using accuracy as the yardstick. You can see a clear split between methods that use optical character recognition, or OCR, which is just converting images of text into actual text, and those that process the visuals directly. The VRAG-RL method, which looks directly at the images, just blows the others away, jumping to over 57% accuracy compared to the next best at around 37%. This massive improvement holds for both smaller and larger models, showing the power of this new framework. So we've seen that VRAG-RL outperforms other methods, but this next table helps us understand why. It's an ablation study, which is where you take a model apart piece by piece to see how much each component actually contributes. If we look at the results, removing the special RAG-specific reward causes the accuracy to drop from 57.1% all the way down to 49.3%. And if we take away the visual perception action space, that ability to zoom in, accuracy also drops, down to about 55%. This breakdown clearly shows that both the tailored reward function and the visual perception capability are essential, working together to achieve those top-tier results. And we saw from that ablation study how important each component is. This next chart really highlights the benefit of the improved retrieval process. The metric here is recall at 1, which, in simple terms, measures how often the model finds the single most relevant image on its very first try, across all 3 benchmarks. Slide VQA, VDSeq, and long bench, you can see that VRAG-RL consistently has the highest score. Getting the right information right from the start provides a much better foundation for the rest of the reasoning process, which is a key reason for its overall success. Of course, all of that improved performance and better retrieval does come with a trade-off, and that's latency. This chart breaks down the average number of actions each model takes to reach a conclusion. You can see that for vanilla RAG and React-RAG, the process is just a mix of searching and answering. But for versus VRAG-RL, there's that extra step, the orange perception block. This represents the model taking time to zoom in and analyze image details. It means versus VRAG-RL takes more steps overall, but as we've already seen, that extra work is what leads to the significant jump in accuracy. While versus VRAG-RL does take a more scenic route to get there, the destination is a much more accurate answer. This research really shows that for complex, visually dense information, the best approach isn't just to search faster, but to reason smarter. By using reinforcement learning to guide its perception, the model learns a more human-like strategy of knowing when to stop and look closer. It's a fantastic step forward for multimodal AI. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.